So hello. So this talk is stopping you from lunch, so we'll be quick. So this talk is about some of the work we've been doing for the past 1.5 years at Spotify, but also it touches upon a lot of work going on in a lot of other companies and a lot of other research labs across the world on this very interesting topic of marketplaces. So this talk is about 3 specific things all joined together. So this is on multi-stakeholder platforms, one. The other one is on machine learning models, and the third one is marketplaces. So as such, we're going to divide this talk into 3 different parts. The first part is just a brief introduction to multi-stakeholder platforms, and we're going to talk about what the stakeholders and different objectives could be. We're going to look at some 67 industrial case studies, and then we're going to look at some multi-objective ML models to do this and evaluation results. So a brief background about me. So I did my degree in computer science and mathematics back at Pilani, India. Then I was with UCL for 3 to 4 years. In the meantime, I was visiting Microsoft Research, interning them, and then since 2 years, I've been in Spotify. So if you're interested in machine learning for marketplaces or more recently causal analysis and counterfactuals, do feel free to get in touch. So this talk is outlined into these 5 parts, and mostly around 3 different phases. So we're just going to begin with a brief overview of how we have been thinking about recommendation systems in traditional systems. And then we're going to switch to marketplaces and different optimization objectives, and then moving on to multi-objective ranking and evaluation. So just a brief disclaimer, this is not a talk about one paper, one set of experiments and a set of results. So I mean, you're not going to find out deep dive details about one specific model here. So this is more of an intentional decision to do a tutorial style talk. And the idea is like we're going to cover about 140 slides in 40 minutes. So that's huge. So I'm just kind of putting it out there up front. We're going to discuss brief intuitions about 20 plus papers and like talk about 3 different phases. And in the meantime, if you doze off, if you want to come back, then look out for these like yellow boxes with red text. So this is like you're plugged back into your train so that like if you miss 15 minutes of the talk, you can just kind of continue enjoying the rest of the talk as well. Cool. So in the next 5 minutes or so, we're going to look at some traditional recommendation system approaches. I'm going to show you a brief whirlwind view of what has happened in the research community, especially in recommendation systems and machine learning for recommendation systems in the last like 10 years or so. And then I'm going to motivate using this background the rest of the work. So at first, we started with thinking about matrix factorization. So we have users, we have items, we created a matrix of interactions, and then we thought, oh, look, we have a matrix, we can do decomposition of these matrix and get user vectors and item vectors. So the moment I have users and item vectors, I can do a dot product or cosine similarity between those, and then sort by that score, and that gives me my first recommendation system. Then we thought, hey, look, what if we add more information? So from matrices, we go to tensors. So tensor is just an extension of matrix. So if we had some side information about the user or the item, then we expand it into a tensor. We can also do a joint coupled decomposition between a tensor and a matrix. And so basically, we had this work. There is this like first work in AAAI 2010, which was looking at some of these collaborative filtering models using tensor approaches. We had some work around 3 years ago during my first year of my PhD, wherein we say that, look, you can combine users, items, and the task they do on your platform, and then do a joint decomposition of a tensor and a matrix. How you do it, it's beyond the scope of this talk, but then you can, similar to matrix factorization, you can use tensor decomposition and then get your vectors. Then we started talking about like latent variable models. So what we've done is a lot of work in this latent variable model space has gone into in the style of topic modeling and LDA style models from 2003. So what they have done is like, I want to encode a specific intuition about my models. So I may not know what the user preferences are. So this is like a hidden variable, a latent variable, and then I can condition it on different variables, on user context and others, and then try to do some graphical model inference on top of these. So there's a lot of work, a lot of PhDs have kind of went into discovering and providing a scalable solution to these graphical models. One of the very good papers on this is a RecSys 2015 paper on some of the probabilistic models for recommendations. Then we kind of go back to 2013 when this famous Thomas Mikolov paper on neural embeddings and word embeddings came out. So then we thought, hey, look, you can use it to embed users as well. So in that case, what we started doing was we started looking at what are the things users are interacting with, and then we can embed users in the embedding space. Then we thought, okay, we have site information as well, so why not like just users? We also include some context and then learn these embeddings using site information. We also matured into learning these joint user item embeddings. So instead of just having one embedding, I have the user, I have the item, and then I have a parallel network, and then I can train it together and learn these joint embeddings. There is a very nice Wisdom 2017 paper on this joint modeling for reviews and recommendation systems. So what have we done so far? We have started with like collaborative filtering approaches like matrix factorization, and we've ended up with some neural approaches to learn embeddings. So the next step for the research community was an obvious combination that we could do neural collaborative ranking. So instead of just looking at users and items separately in embeddings, we have latent vectors for both of them and then do a joint embedding for both and then come up with these like neural collaborative ranking approaches. So as of 2017, at least on some of these like Amazon review datasets and others, this was one of the state-of-the-art methods being used in a number of different contexts. So we've looked at what these models look like. And just in the next 30 or so seconds, I'm just going to give you some variants of recommendation styles as well. So we've also done work on short-term and long-term profiles. So can we just learn user vectors for short-term user preferences versus long-term? We could look at cold start or cohort-based. Cohort is just a fancy name for groups. So instead of just learning preferences of a user, I learn preferences of a user group and then do recommendations. We can also look at multi-view, multi-interest models. Like the hypothesis here is that maybe your Netflix account is being shared by more than one people. So in those scenarios, if you don't have explicit profile, then can we disentangle these profiles and have this like multi-view models? There is some work on multitask learning as well, that not only you train on one task, but on multiple tasks. So, okay, where are we? Why are we talking about all these things? So there's a lot of work which has gone into developing recommendation system models in the last 10, 15 years, like about 2 decades now. So what do they all have in common? So one of the key things they have in common is they are all user-centric systems. So what do I mean by user-centric? So they have been trying to understand user needs. My PhD was on like understanding user task in search and Cortana digital assistance domain. They've been trying to understand user interest. They learn from user behaviors, user interactions, and then they're trying to develop these personalization approaches. So, and also not just development, but also in terms of evaluation, we have centered on optimizing user satisfaction, measuring engagement, and like user-centric methods. So a lot of work across a lot of these research labs and industry have focused on user-centric methods. So the question we ask is caring about the user enough? So if you look at some of these companies, if you, let's say, pick up like Uber as an example, right? Uber not only cares about getting me the ride in the earliest time or in the cheapest price, perhaps not the cheapest price, but Uber cares about getting rides for all drivers as well. So Uber as a platform would fail if I as a driver don't get any ride for the entire day. So the moment you start thinking about, okay, what should these companies be optimizing for? Then we start considering this question that maybe it's not just about the users, maybe it's about other stakeholders as well. So this is where we come on to this current talk, which is we have multiple stakeholders in a lot of these like new emerging multi-stakeholder platforms. And the customers is first and foremost the user. We want to keep the users happy, but it's also about like taxi riders, or if you're Airbnb, then you want to kind of give preferences to your host or guest. And if you're, let's say, Deliveroo or UberEats, then you want to keep in mind that you have these delivery partners as well. So each rider should get some delivery jobs as well. And the platform itself, like you cannot like sustain a platform if you're not kind of making profits or benefiting from some of these recommendations. So if you take a holistic look, then it's not just about users. It's a lot about how do we make sure all the stakeholders are happy in our recommendation settings. So as such, one of the hypotheses I want to convey here is this, that if you're just thinking about user-centric methods, maybe it's not sufficient to serve recommendations in such scenarios. Cool. So with this background, I'm just going to briefly, in the next 3 to 4 minutes, talk about marketplaces. I'm going to define marketplaces and then build on top of it for the rest of the talk. Any quick questions? Cool. OK. So a marketplace is nothing but an intermediary which helps facilitate economic interaction between 2 or more agents. This is just like one of these Wikipedia definitions. But then marketplaces have been around for a while. I mean, if you go back my hometown in India, these have these supermarkets, like markets on the road, wherein they have these villagers selling food. You can go and buy these fruits and vegetables, or you can go to a mall, or you can go to a New York Stock Exchange and kind of waste a lot of your money in betting on bad stocks. So all of these are markets. And so markets have existed. But if you look at some of these modern analogs, then they're coming up in a lot of different topics. So be it education, be it consumer goods, be it recruitment, be it construction, logistics, B2B, home services, hospitality, delivery, finance, transportation, health, beauty, design, photos, food, and everything. So this is what drives home the point, that a lot of these billion-dollar unicorn companies coming up are these marketplaces. And when we have been thinking about these recommendations models, we have been mostly focused on making users happy. So this is why we've been investing a lot of time and effort and research on understanding, okay, what are the different research questions around how do we support these marketplaces? And so there's a misnomer. Marketplace, you could think of marketplace as like, hey, look, the kidney exchange programs back in the US in 2003, that was one of the first major marketplace which won the Nobel Prize in Economics back in 2012. But a lot of these systems are multi-stakeholder platforms. So in my talk today, we're just gonna analogously talk about multi-stakeholder platforms and use marketplace to denote those. And they have evolved over time. We've started with offline stores to online to task-based marketplaces to skill-based marketplaces and professional services more recently. So these marketplaces have been thoroughly evolving. So we need to evolve our models as well. So one of the key kind of insights here is that the success of any platform, right? If you're connecting multiple stakeholders in your platform, then you have to do very well in matching. You have to match the consumers and suppliers and all the other stakeholders, and this leads to recommendations. So this is where the talk has all the background context we need. So we spent about 10 minutes putting all the background in together. So we need to develop recommendation models for marketplaces which can connect multiple stakeholders together in an efficient way. Okay, so when we start talking about these multi-sided platforms, and the problem is you're not just balancing users with suppliers. You're balancing users with your own company objectives, or there could be other suppliers as well. So if you're, let's pick up the example of UberEats, then they have the restaurant partners, they have the delivery partners, they have the users, and they have how much profit the platform itself makes. So this is not just a trade-off between two objectives or two stakeholders. This is a more nuanced balancing problem. So if you look at some stakeholders, and the stakeholders could be the user, it could be drivers, advertisers, campaigns, hosts for Airbnb, platform providers, and for each of those you have these metrics you want to do well upon. So the moment you have these things, then again, this typical recommendation strategy does not work. So what is this like? Let's take this example of a Spotify homepage. So we have a few playlists, and we want to recommend some playlists to the user. So if you just care about user satisfaction, I'm just going to pick up this, hey, look, just pick up this one objective, which is minimize user annoyance, and then just optimize for it. So this is simple. I don't care about anything else. I just minimize user dissatisfaction and then serve my recommendations. But this is not meant to optimize different objectives. What we need in a multi-objective, multi-stakeholder scenario is something like this, that I want to optimize a function which has multiple constituents. Now, each of these stakeholders could give you one or more objectives. If you just look at users, right? I mean, you can optimize for user clicks, user engagement, user return rate. You want to minimize the time user is away. So there's a lot of metrics just on the user stakeholder. And other stakeholders bring in their corresponding objectives and metrics as well. So in all this setup, we're not looking at a model which just optimizes one thing. We're looking at a model which optimizes multiple things together. And this is where, ideally, if you're doing it right, if you're doing it by proper principled machine learning approaches, you should find the Pareto optimal front on some of these objectives. So I'm not going to talk very heavily detailed on finding the Pareto optimal solutions, but the ideal solutions are going to be Pareto optimal. So by Pareto optimal, what we mean is something like this visual diagram on your right, that if you have two objectives, then the red dots are the dots which optimize for both, and these are the best possible solutions you can have. Now, where on this red line you want to be, that's your business decision. So if you just care about objective 1, just go to this point H. If you just care about objective 2, just go to this point A. So if your machine learning models are able to provide you these Pareto optimal paths and curves on in the space, then you can use your business decisions to guide, okay, what kind of recommendations do we actually want to serve. So with this background, 15 minutes into the talk, I'm going to focus on two different parts in the next 15 and 15 minutes. So the first part is just a brief, quick overview of different stakeholders and what does it look like for different types of companies and what their objectives could be. And then I'm going to briefly talk about some methods for multi-objective recommendations. If time permits, we're going to look at some evaluation. So the summary so far, this is not yellow and red, which should have been. But if you've been sleeping, what we've been just summarize here that traditional recommendation systems are not suited perhaps for marketplaces. And we need to consider multiple objectives. And we need to have these models which are looking at and considering all these objectives together. So if you're looking at some stakeholders and their objectives, I'm going to quickly walk through some 7 case studies. These are all companies which all of us have either worked on or use on a daily basis. So let's just pick up UberEats. So UberEats are different types of, it's a 3-sided marketplace. So there is this very amazing blog post, which I really encourage you to go and read on how UberEats has been thinking about their recommendation model. So they have given like a very nice time frame of how they have evolved their thinking from just focusing on users to like a multi-objective realm of optimizing for each of these 3 stakeholders. So the key thing over here is that if you don't have enough eaters, then restaurants won't participate. And if you don't have enough restaurants, then the selection available to an eater decreases. And if your order decreases, then the delivery partners earn less. So basically, there is this like complex interplay between these 3 stakeholders, and an unbalanced market demand-supply dynamic degrades the overall value of the platform in itself. So it's very important for these platforms to make sure that they are kind of keeping in check how the interplay is functioning on their platforms. So some of the potential objectives, like really quantifying some of the things which they can optimize for, is like eater conversion rate. So conversion rate could be like how many times does the user come onto your website and actually orders food. It could be diversity, that eater explores different types of food. It could be exposure of restaurants. So maybe there is this like very famous restaurants in somewhere in Stratford which is not getting exposed at all. So then those tail suppliers, tail retailers, tail artists won't get enough exposure. So we want our platform to consider these in the objectives or in their constraints somewhere. It could be earnings per delivery partner, pickup times, distances, delivery times, a lot of other things. So I can just develop a recommendation model for UberEats on any of these 1 objectives as well. But that will hurt or maybe not be optimal for the other stakeholders. So that's why we need these multi-objective models. Same, so UberEats is a specific case. You can go and look at like different on-demand delivery platforms for groceries, restaurants, retailers, stuff, and the same principles apply. You can also look at Etsy, which is a marketplace for craftsmen. It's pretty big now, about 2 million active sellers and about 32 million active buyers. And again, like you have buyers, sellers, and the platform. For Airbnb, you have guest and host, and you want to make sure that your guests are getting the homes they want, and if I'm renting a room, then my room is also getting guests. So there's also this like a Medium post by Mihalo. He's a researcher who was at Yahoo before, and now he's with Airbnb. So they have done a very nice study, and they've kind of given a lot of these A/B test results on how they have been thinking about these joint optimization and what kind of objectives have they been thinking about. So one of the very nice things about this is that they've been also thinking about, let me just see. Yeah, so they've been thinking about that if there is a new hit, like if there's this really nice fancy room near Buckingham Palace, which was not on the platform until yesterday, then how do we kind of enable discovery and promoting of this like new hit earlier? So if your model does not encode this explicitly, then you're not going to do that. You're going to miss out. You're going to wait for enough users to go and find that room, book it, give it enough ratings, then those features are going to get populated, and then your model will become aware that yes, this is something nice to recommend. So that's why it's very important that you might have different business goals, and if one of the goals is to just pick up these new things earlier and quicker, then you have to encode these things into your model. So at Spotify, we have been thinking about some of these same things from this artists and fans perspective, that we have these artists who are musicians and also like podcast content producers as well. And we want to kind of develop platforms which match artists and fans in a healthy ecosystem. So that's the use case for Spotify. In our SEC filing, we have mentioned that we want to be a marketplace to enable artists to kind of live off their earnings from Spotify. For P2P lending as well, this holds. Like you have lenders, you have borrowers, and you have a platform. And a platform has inherent incentives in showing one lender to a borrower versus other. If you're looking at Funding Circle, which is a peer-to-peer lending platform, then they also have their different objectives. Like they want to give quick and easy access to loans. So just take a pause over here, right? If I say quick and easy access to loan, right? This is not just an English term. What exactly is it? Is it like for each listing, it is time since when this listing has been on the platform? So if for each item you can potentially show on your recommendation page, you have this feature or this objective of minimizing the time, then your ML model or a simple sorting model would be like, okay, what's the time? And then sort by decreasing value of time. So when I use these like free and easygoing English terms, there is like quantification behind all of these things. So each like return on investment is something which they need to quantify, they need to predict. So each of these objectives are not just some English words which are like very easy for us to quantify. Like if you're looking at diversity on Spotify, or if you're looking at exposure for artists, it's a very hard question. Like, okay, if an artist has been on Spotify for like 2 years now, and they have like, let's say 4 tracks, do we give them enough exposure as somebody who's been on the platform for like 10 years and they've had like 40 songs? We don't know, like what is the right exposure equality for Spotify to maintain? It's very easy for us to say, hey, let's be fair to all the artists and expose them equally. But how do we define fairness? How do we define exposure? Like we have to condition on, are all these artists equally relevant in the given context or not? So it's very easy for me to list down one line over here and say, look, you can additionally optimize for it. But then developing the right mathematical function to quantify these objectives is a very hard problem. So this is like all the nuances which go into defining some of these objectives for your ML models. Similar for crowdfunding, just a quick example here. Like we have 3 types of crowdfunding examples, campaigns here. One is this like fancy drone which you can buy for about, what, $100,000 or something, $7,000. There is this art piece which you can buy, and there is this like a medical emergency crowdfunding issue here. So imagine like if you go to some crowdfunding platform, then which of these 3 will be on your top banner page? So this is a very important business decision. Like if you look at some of these health issues here, if you want people to go and donate and crowdfund to those initiatives, then your objective has to be around this nice concept of like social welfare. If that's not the case, then like if you're just matching user preferences, then maybe for me you'll just show this drone, and for somebody interested in us, you're going to show this. So it's a lot of very subtle thinking around how do you quantify these objectives into your system and recommendation models. Again, like there's this bunch of objectives. So basically, if you just take a step back, if you're a marketplace, or if you're a researcher doing generic research about marketplaces, then there's like the sea of optimization objectives which you can potentially optimize for. And we just divide them into 3 categories: user-centric, supplier-centric, content-centric, and business-centric. So the important thing over here is to understand the interplay between these objectives. The simple thing could be, in a happy world, all these objectives are like positively correlated with each other. So if you optimize for one, it helps the other by default. So I don't have to do anything. If I just look at users and user satisfaction, then I can just look at clicks and dwell time and engagement time. So if clicks increases, people are going to spend more time, engagement increases, so I don't have to unnecessarily additionally optimize for engagement as well. So if your objectives are correlated, then you are in this like nicer world, and you don't maybe need to resort to some complicated ML models. It could be neutral, like optimizing one doesn't really impact the other. Or it could be anti-correlated. When you're optimizing for one, it hurts the other. A couple of examples is this is some work we did at SICM conference about 2 years ago, actually last year. So this is like, we're kind of starting to walk in this path, like how do we create a fair ecosystem, a fair marketplace? So we picked up 2 objectives, like relevance of a track or of a playlist to a user, and fairness, which is like diversity to the artist. And we just plot over here let's just pick up some random 10,000 playlists on Spotify. And let's just say we plot the fairness, like the diversity estimate to the artist, and the relevance over here. The key thing to note here is that there is nothing on the right top. So there are very few playlists which have high relevance and high fairness to the artist. So that means like optimizing for relevance would not do well on your fairness. Optimizing for fairness would not do well on your relevance. So this is like a very simple use case. Like I cannot create a system without putting thoughts into it. Like if I just optimize for relevance, which most of us have been doing for 10 years now, we are going to hurt your suppliers and retailers. Let's just take a more nuanced look at these. Let's just consider more user satisfaction objectives like click streams, items consumed, stream time. And let's start looking at some of these diversity estimates. And additionally, let's say we want to promote some group of artists. Like we say that, look, we are launching in India, and we want more Indian artists to get exposure. The key thing over here is like different SAT objectives. SAT is a short form for satisfaction. They're correlated with each other. So if I only care about satisfaction, I'm in this like rosy world that, yeah, I mean, all of this would kind of benefit and help each other out. Supply diversity as such is almost neutral with some of these satisfaction metrics. And promotional objectives really hurts the satisfaction metrics. Now this is where actual problems come and arise. Like you have your system, as a platform, you want to make money, you want to promote different artists, and you want to have this like very nice distribution of, you don't want tail artists, you don't want tail retailers who never get exposed. You want this like flat tier that everybody's like equally exposed, and you care about user satisfaction. So in this world, we need to consider what do we optimize for and how do we do it. So a brief summary that we've talked about some industrial use cases. Most of these companies and platforms have often conflicting objectives, and we need to model the interplay between these objectives. So the question would be like, how do we, like we have to carefully decide what a system optimizes for. And how do we optimize multiple objectives? We're just gonna talk about it after I manage to open this portal. Cool. So we have quite a few approaches of doing this. Like we have some simple approaches to some complicated. So it's not to say that one works better or one works like bad or something like that. It's more about what is well suited to your needs. It depends on what kind of objectives you have and how they are kind of competing or what the interplay is between those. We're going to look at some of these in at least one of them in a good detail, others in like brief, insightful overview style detail. So one of the first things you can do is like just balance two objectives together. So the easiest thing to do is, let's say I care about relevance, which is F1, fairness, which is F2. Then what I can do is, first of all, I forget about F2 and just optimize for F1, like just maximize relevance or maximize fairness. Or maybe probabilistically decide I'm going to flip a coin, and for some users I'm going to optimize for relevance, for the others I'm going to optimize for fairness. This is not what we do at Spotify. But you can start then thinking about how do we do these trade-offs. So one of the easy ways of doing trade-off is just a linear combination, right? A linear combination would just give you an aggregation that I'm looking at two functions, and I just have a linear weight of combination of these two functions. Now, the problem over here then becomes this parameter beta is a hyperparameter, and then you'll have to go and find what's the best value of this hyperparameter, which gives me the balanced ecosystem I want. So there's a lot of work which has gone into these aggregation functions. We have looked at a weighted sum. You could also look at some of these like ordered weighted averages and regret style approaches if we want to kind of dive deeper into what kind of aggregation functions we could use. There's a lot of work which has gone into multitask learning. And in here, so if you go back a few slides, if you think of those user satisfaction objectives, then some of these objectives was clicks, whether the user will click or not, stream time, how long will the user stream this track, return rate, will the user return back or not. So these are all like predictive tasks. And the moment I have multiple predictive tasks, I can go and resort to multitask learning. So in a multitask learning, what we do is we have two tasks, and we want to minimize the loss for both of these tasks. So this is like a very hard parameter sharing problem. Like if I have these two tasks, then both of these layers are shared, and then I jointly optimize the loss function for these two. Or I could do some soft parameter sharing. When I say soft parameter sharing, let me see if it works. Yeah, so what we do is we say that so over here, we are kind of necessitating that these two layers are just the same, they have the same weights. Over here, we encode it in the objective, in the loss function, that I want to minimize my difference between these two layers and these two layers. So the model is trying to keep those similar while they're learning both the tasks together. So multitask learning has evolved in the last 5 years, and most of the state-of-the-art methods in a lot of these computer vision and NLP domains have shown that multitask learning systems are kind of more or less the state-of-the-art in these tasks. So this is just like a very hand-wavy definition or intuition about what multitask learning does. Few papers have come up in the last few years. This is a very recent AAAI paper from Sebastian Ruder. He's one of the pioneer researchers who was in Dublin doing his PhD until 1 year ago. So this is sluice network. So basically you say that, look, I have my shared layer, I have my task-specific layer, but I also have something in between. And I'll let, instead of me deciding how the parameter sharing should happen, I will let the model decide how to share parameters based on how related the tasks are. So some of your tasks could be related, so then they might want to share a lot of parameters. Some of the tasks may not be related, so you better avoid sharing a lot of parameters here. There's some work on joint many task models. You're not just doing 2 tasks, you're doing a bunch of tasks, and this is a very nice paper on NLP tasks like chunking, point-of-speech tagging, entailment, and this is kind of performing, multitask model in NLP performs better than single task models. There is this very nice work at CVPR in the vision community from last year, wherein if you have multiple tasks, then remember we always had this beta parameter, be it in the relevance score sorting or be it in your loss function. You have to weigh the different tasks together. And how do you weigh it? It's a very challenging problem. It's like a proper hyperparameter search problem. So these guys advocated the use of uncertainty, like how uncertain is my model, and then use that to define the weights of how the different losses get weights together. So this was kind of showing some very good performance on computer vision tasks. And then you can also start thinking about hierarchical multitask learning. This is again a very recent 2019 paper that you can, okay, forget about this. Let's just consider user satisfaction with Spotify, right? I can train a model just to predict, are you going to skip this track or not? Now this is a very base task. I could use this task for any other thing. Like if I want to know that, will you be interested in this playlist or will you be interested in this type of artist? I could still use my base model. The base model was, will you skip this track or not? So there are important learnings you can have from your base tasks which are very generic, which a model should anyway be aware of. So this is the intuition which goes into designing these hierarchical systems, that you have to do good on, let's say, this task here at the top. And after you've learned it, you should kind of use that knowledge as a short circuit to your other tasks as well. So this is not just like one after the other. You're short circuiting like things from top until to the bottom as well. So there's like a lot of business need and business motivation in designing these hierarchical multitask systems. So we have 10 minutes, and we have looked at scalarization multitask learning. There is this very nice paper I don't have the time to go into at all, but we've been experimenting with multitask learning as a multi-objective optimization, and this is a NeurIPS 2018 paper. There is a follow-up paper at NeurIPS 2019, which is gonna, like the conference is gonna happen in December. So they've posed multitask learning as a multi-objective optimization problem, and this we've kind of, on our experiments, we have implemented and tried this. So we've seen better performance on these from this model as compared to some of the other models which we previously talked about. I'm gonna skip this. The reason is like, it's gonna take more than 10 minutes to walk through the details of this. A couple of other things around multi-objective recommendations and how do you think about these problems. So we have been working on Bandits, and there's some work on multi-objective reinforcement learning. Okay, let's just pause for a while. Why are we even talking about all of these things? The reason why I'm mentioning this is like I have 10 minutes and I want to give you an overview of what kind of tools you have in your arsenal to attack your problem. So if you really have simple problems, non-negatively correlated, like positively correlated objectives, just go with scalarization. Or if you have easy prediction tasks, just go with multitask learning. But the moment you reach there, then your system matures and you say, oh, this is not going to work well for the next use case. So this is why we evolved and matured into talking about some of these bandit works and RL. So we have this paper at RecSys last year, which is Explore, Exploit, Explain. So in this paper, we've been talking about how do we use contextual bandit models for explainable recommendations. So if you go to the homepage of Spotify, you were being served recommendations from a bandit model. So we had a contextual bandit model in production for 99% traffic at least. And so you see these this explanation, like your daily, like made for you is one of the shells you have on Spotify. Or it could be like your personal favorites, or because you listen to this. So these are explanations which Spotify provides to you in addition to your recommendations. So how do we balance recommendations with explanations and exploration exploitation in the bandit setting we describe in this paper? So a quick time check. So what we did was we built on top of this model. This is just like a single objective model, just considering user satisfaction as an objective. And what we've done in the last year is we've expanded on it and made it a multi-objective contextual bandit model. So I have 10 minutes. I could skip to evaluation or go to like a 5-minute deep dive into bandits. So I'll do a quick show of hands. How many of you want to do the deep dive? Okay, and how many of you want to skip to the evaluation? Okay, that's about 60, 20, and the rest 20 are neutral. Okay, so how many of you know bandits, like some intuition about what bandits are? Okay. This is going to be very rushed. So basically, imagine if you're in a casino, you have these slot machines. And let's say you have like 5 slot machines. You go in a casino, you pull an arm, and then you get a reward. So if you have 5 of these slot machines, if I pull the first arm, the first slot machine, I get, let's say, $5. I go to the second one. I pull the second arm machine, I get $10. Now I have a decision. For the third time, should I go to the new slot machine, or should I just exploit the 2 machines I've tried? Maybe the first machine just gave $5 for the first time. Maybe it could give 50. Or maybe the second machine, the maximum is 10. The next time, always you're going to get less than 10. So you always are in a dilemma that should I exploit? I know this machine is giving 5 and 10 at least. Or should I explore that I've not tried these 3 things out? So this is the logic behind some of these multi-armed bandit models. So you have an action to take. Which of these slot machines should I pick? So on a Spotify playlist ranking on homepage use case, you have a number of playlists we could show to you. So for each user, we have, let's say, some few hundreds of candidate playlists we should show on your homepage. Now we start by taking an action. You come in, and I decide, like, okay, from among these 200, which action or which playlist should I show to you? I make that decision, and you give me a reward. You say that, no, I didn't like this playlist, or you stream for like 2 hours on this playlist, you saved and hearted a few tracks. So this is like a very good reward for us. So this is how a model learns that which action is useful, and how we do it is like we kind of minimize regret or maximize the reward which the system obtains. So this is a traditional bandit model. A contextual bandit model basically works by observing a context as well. So the key difference between the two is that in a contextual bandit model, you observe a context. What is the context? Context is, okay, who are you? Like, what have you liked in the past? What time of day is it? What kind of music profile do you have? What kind of playlists have you created? What kind of songs have you skipped? So we have a lot of context about you the moment you enter this homepage of Spotify. So this is the context, and now we can take an action condition on the context. So the difference here was I'm just taking an action without knowing your context. But in a contextual bandit setting, I'm taking an action condition on the context. This is nothing new. People have used it for like more than a decade now. So what we did, okay, so this is just a brief background on bandits. How do we extend bandits to multi-objectives? There's some work, really, really recent work at ICML, AI Stats, which have gone into making these bandit models multi-objective, but they've mostly worked on normal bandits, not contextualized version of these bandits. So this is where like we did some recent work on like creating multi-objective versions of these bandit models, of contextual bandits. So this is like, so far you know that we've been working in this paradigm where we have multiple stakeholders and multiple objectives. The moment you have multiple objectives, what we propose is you can use something called GGI. So GGI is like a very old term which statisticians have been using to measure income inequality. So what basically GGI does is it's an ordered weighted average that it kind of prefers equal allocations. So if you have multiple objectives, if you encode a GGI function on your objectives, then you get more equitable distribution of the respect each objective gets. So basically, this f of pi 1, pi 2, pi 3, pi 4 could be replaced by this Gini function. And this Gini function, trust me, for now, is just going to magically prefer equal allocation. So with this slight trust, let's just spend 2 minutes on what's the actual algorithmic strategy. So in a bandit setting, because we are in a contextual bandit setting, the goal is to find an ARM strategy. So what is an ARM strategy? It's just a fancy way of saying, look, I have a few playlists for you. What is my playlist selection strategy? So in a bandit setting, I will just call it the ARM selection strategy. So effectively, after we have done all this like ML modeling, I want to, for each user, for each context, I want to have this strategy based on which I select the playlist for you. So that's the goal. So at each round, you comment on the Spotify, we observe some context, like what is the previous session about, what time of day is it, where are you logging in from? We don't have locations, so we don't know where you're logging in from. But then like we have a lot of context about you. So we have this context, And then if we choose an arm, which is if we choose a playlist, then we assume that we get a linear reward. So you're going to either skip tracks, or you're going to stream a lot, or you're going to save some tracks, or if you're just going to abandon Spotify and just go away. Hopefully not the last case. So when you do this, we observe these rewards, so we know like, okay, how good or bad did we perform? And the key thing over here is we get vectorial feedback. What is the vectorial feedback? In a single objective model, I just get one feedback. I care about user satisfaction, so I just get a value how satisfied the user was. In a multi-objective scenario, I get vectorial feedback, because if I had 3 stakeholders and 3 objectives, then I get a reward of vector 3. So now we get a vectorial feedback, and what we do is, basically the difference is, if I had known what the best arm is, then I could just do a brute force search. For each user, for each context, I just kind of go wild and find out the best possible playlist. And then, because I know what the reward could be. The problem is, the reward is dependent on context. Like, you might listen to a track now because you're in the office, but if you're on a Friday night in London partying somewhere, then you won't listen to that track. So that's why, because we don't know what the reward is, because the reward is conditioned on context, so then we want to maximize our prediction problem. And this is where the Gini function we've been talking about, this comes into over here. So for all the k objectives we have, for all the rounds, we want to maximize the Gini index formulation of that function. So I'm going to skip the details of this. So basically, a one-line summary over here is 2 things. One is, we have developed a multi-objective contextual bandit model, which looks at multiple objectives, so multiple rewards, and then decides, okay, which arm or which playlist to show. But what we have done in this room in the last 15 minutes, we have looked at quite a few machine learning approaches, from really simple linear scalarization, layered combination, A1W1 plus A2W2, to multitask learning, to possibly some of these multi-objective bandit models. So does it even work? So I'm just going to quickly present some quick results on these. So let's just present the use case of looking at just interaction-based metrics. So I just focus on user satisfaction, and I consider clicks, streams, total number of songs played. So what we find over here is that if you're, of course, like one of the first results is, if you optimize for clicks, then the click metric is higher. If you optimize for stream time, then the stream time metric gets higher. But the key result over here is, the moment we do a multi-objective bandit model on top of it, then that model beats all the other models. And this is not just for one metric, this is for all the 4 metrics which we considered. So a multi-task model, I mean, this is a hypothesis. Like, the model we tried this on was a multi-objective bandit model, but the intuition over here is, if you're jointly optimizing for multiple correlated metrics, then your model might learn new associations. So if you look at clicks and streams, a click has to happen for a stream to happen, right? And a stream has to happen for a long session to happen. So there is this inherent chaining structure present in your objectives, which a multitask or a multi-objective model can learn from and do better for each of these metrics. So basically, the summary over here is that optimizing for multiple interaction metrics is better for each metric than directly optimizing for that specific metric. So even if you don't care about marketplaces, multi-stakeholder platforms at all, if you just care about your users, then I would make a claim, but argue for jointly optimizing all user satisfaction metrics together. Let's just start adding some competing objectives. So what if we add a business objective, say gender of exposure? So what if we want to be kind of pick up a gender and then try to expose that more? So this is some promotional objective. So what we see was, we get gains in business objectives, which is like we get gains in more promotional without much loss in user satisfaction metrics. So this is a very important point because it may not be a zero-sum game. Music as a domain might allow for some users to be more okay with like listening to more diverse tracks. So your domain might not be like, this is not necessarily a trade-off, right? It's not that you're just hurting the users and benefiting the other artists. It might be that you can increase the whole pie, and then everybody becomes happy. So this is what the real motivation is on why we want to explore these bit more nuanced ML models. That can we increase the pie? Can we not hurt the users while at the same time benefit some of these like niche artists? So one of the hypotheses which we're presenting is, maybe it's not a zero-sum game. Maybe we can get gains without hurting some of these user-centric objectives. We tried a bunch of other baselines and some other published approaches, and we found out it's not just about doing multi-objective ML. So the takeaway is not hey, look, let's just do multi-objective, and any multi-objective would work better. So we found out how do we do actually these multi-objective modeling matters a lot. So we have to kind of put in some careful insights into how do we go about doing these things. So that's the summary. Again, just a repetition of the 3 points. I have a few FYIs in the last 10 seconds. As part of Spotify, we have released quite a few public data sets. So if you're a PhD student, which I was until 2 years ago, and if you don't have any data to work with, so we have released this data set on 1 million user sessions. This is one of the first session level data with user interaction available on the internet. So we have 1 million user stream sessions, which are anonymized, and we get for each session, we have user feedback available as well. And we have this also 1 million playlist data set, which is publicly available as well. We have been doing this tutorial on recommendations in a marketplace. I gave you a very condensed 45-minute introduction to this. We've had this tutorial at RecSys this year. Is going to happen again next year in one of these conferences. It's a 3-hour more longer tutorial. There's one happening in search solutions on Monday. So if you're really, really working on these problems and interested, and if you're okay with paying $90 for it, which I may not advise you to do, so there is this tutorial happening on Monday. And yeah, we are hiring. We're hiring data scientists, research scientists. We're hiring ML engineers, data engineers in Stockholm. We're based in Stockholm, in London, in Boston, in New York. And that's the summary.